Okay, guys, so what you see on the whiteboard is an exercise similar to the exercise number 4. It is not the exercise 4. I always specify because I don't know why in your homework, in the place where it's supposed to be your exercise, it appears my example. So when that happens, I take 1 point away, or 2, depends on how much the exercise costs. Okay, so this is not the exercise from the book. This is not from the homework. This is just an example. Okay, so this example is based on the exercise 4 from the page 51. Okay, it says that a driver of a car traveling at 15 meters per second applies the brakes, causing a uniform acceleration of -1 meters per second squared. How long does it take the car to accelerate to a final speed of 5 meters per second? How far has the car moved during the braking period? So, you can make a sketch just to represent the situation. We have a car. A fancy car, okay? It's traveling at a speed of 15 meters per second. What is this velocity, initial or final?
Initial.
That is correct. This is the initial velocity, and it's equal to 15 meters per second, okay? It says applies the brakes, causing an uniform acceleration of -1 meters per second squared. So when it says applies the brakes, I know that the velocity is going to be reduced, okay, because it says applies the brakes. When you apply the brakes, it's because you want to slow down or you want to stop. And that goes opposite to your position, okay? That goes opposite to what your initial motion was. So it says acceleration of -1.5 meters per second squared. What is that?
Acceleration.
Yeah, it's pretty clear that it's acceleration, okay? Now, it says, how long does it take the car to accelerate to a final speed of 5 meters per second? That means I will apply the brakes, but the car is not going to immediately stop, okay? It requires some time to stop or to slow down to the desired velocity. In this case, my desired velocity is 5 meters per second. So I need to know how much time passed between 15 meters per second and 5 meters per second under a constant acceleration of -1 meters per second squared. And then it says, how far has the car moved? How far has the car moved? What else I'm going to look for besides the time? What else I'm going to look for?
Displacement.
I'm going to look for displacement. Okay, so in this topic from the page 51, it is actually velocity and displacement, okay, with constant acceleration. So we have a formula for both. So to find the time, I can use one equation or the other, okay? It's gonna depend on what I have. So the problem is giving me initial velocity. So my given are initial velocity of 15 meters per second is given me a final velocity of 5 meters per second, and it's giving me an acceleration of -1 meters per second. Okay, I'm looking for time and displacement. In what units I'm going to leave my time?
In seconds.
Okay, time, that is going to be in seconds. And in what units I'm going to leave my displacement?
Meters.
Meters.
Okay, very good. Now, What comes after? I need to see if I have a conversion to do. Do I need to do a conversion here?
No.
No. No, take a look at the units. I have meters second, meters second, meters second. These are squared. So, no, I don't need to do conversions. So, my first step, I'm not gonna do it. But I know that I have two formulas to use. I know that I have final velocity equals initial velocity plus acceleration time. And I know I have one for displacement, that is displacement equals to initial velocity time plus 0.5 acceleration time to the second power. I have those two equations, okay? So let's analyze what I have and what I need. I have the two velocities. I have acceleration, okay? I have the two velocities and I have acceleration. I need to find time and I need to find displacement, okay? So from the two formulas that I have, I need to see which formula works better for me. What is going to be easier to isolate, okay? So I need to solve for the unknown. What is my unknown?
Time and distance.
Time and displacement, okay? Now, which one I need to find first? Time or
Time.
displacement? The time. Why the time? Because I need the time here, okay? And I need the time in the other side. If I find displacement, okay? If I find displacement, I don't have the time, so I cannot find it. But if I find the time and then I find displacement, I will be able to do that. So first, it is necessary that we find the time. So my unknown in this case is going to be delta t. And I will isolate for the time. So I have my main equation as B final equals initial velocity plus acceleration time. And I will isolate for the time. First, I'm going to move this term to the other side. What is this term? What is initial velocity doing over here? Is adding, subtracting, multiplying, or dividing?
Adding.
So initial velocity is adding. And when you send it to the other side, it's going to be subtracting. So the equation is transformed into final velocity minus initial velocity equals to acceleration time. Okay? But you still need to isolate for the time. What are you going to do? You need to move the acceleration to the other side of the formula. What is acceleration doing to the time? Is it adding,
Multiplying.
subtracting? It is multiplying. So acceleration is multiplying here. When you send it to the other side, it's going to be dividing.
Dividing.
Okay? So the procedure will be final velocity minus initial velocity divided by acceleration equals time. And now that you have the equation already isolated for the time, we're going to solve for it. Okay? So I'm going to work in the other part. What is my final velocity in this problem? My final velocity is
5 meters per second.
5 meters per second. This minus is from the formula. Okay, now what is my initial velocity?
15 meters per second.
15 meters per second. All this is divided by the acceleration, that is -1 meters per second squared. All this is equal to the time, and we see 5 minus 15, how much is that?
-10.
-10. It is important that you don't forget to write the sign. If you forget, it's going to give you a negative time. And remember what I told you about the negative times. So 5 minus 15 is going to give you -10 meters over second divided by -1 meters per second squared. This is equal to the time. Now take a look. My two negatives are going to be canceled. 10 divided by 1 is going to give you 10. Now in what units are going to be this?
In seconds.
Meters and meters are going to be canceled. And this second from above is going to be canceled with this one from here. So the remaining unit is going to be seconds. So with this, we solved one part of the problem. How long does it take the car to accelerate to a final speed of 5 meters per second? Well, it takes 10 seconds to reach the speed of 5. Now it says how far has the car moved during the braking period. So for how long does the braking period occur? It occurs for 10 seconds. So how far has the car moved? I'm going to use the equation for displacement. Okay, so my first unknown was delta t. My second unknown is displacement. And my formula is, I already have a formula for displacement. I'm just going to copy and paste. Okay, displacement is equal to initial velocity time plus 0.5 acceleration time squared. So all I do is I replace by my givens. Initial velocity, that is how much? How much is my initial
5
velocity?
meters per second.
The initial velocity?
15 meters per second.
15 meters per second. How was the time?
10 seconds.
10 seconds.
Plus 1/2. Acceleration is
-1.
-1 meters per second squared. And the time, that is 10 seconds. But this time, be careful because this time is raised to the second power. Okay, so from here, you obtain 15 multiplied times 10 is going to give you 150, right? Do you get 150?
Yes.
Okay. Seconds and seconds are cancelled. Seconds and seconds are cancelled, so my remaining unit is going to be meters. Okay? So here I have 150 meters. Okay, plus. And now I'm going to solve for this. 0.5 times -1 times 10 raised to the second power. How much is that?
-50.
Okay, -50. Here, the cancellation of units. Second square is going to be cancelled out with second square from the other parentheses. So it's going to give me meters. -50 meters. So here, you have plus and minus. Plus and minus. What do we do here? What happens when you have plus and minus? What symbol do you write instead?
Subtraction.
Subtraction.
Okay? So here, you're going to have 150 meters minus 50 meters. So the displacement was 100 meters. So how far the car traveled during the braking period? The car traveled 100 meters because the car didn't completely stop. Okay, when an object is moving, it's really hard that that object starts immediately. That's why many accidents occur. For example, in Yohoa, the Peaje de Yohoa, I think you have heard that many accidents have occurred over there. That is because of that. It is really difficult for an object to stop once the object is moving. And that's why car accidents happen, okay? And that is related to one Newton law that is called the inertia law, but we're going to talk about that later, not yet. From the homework, do you have any other doubt? Was it difficult, the exercise 4? It wasn't. It wasn't difficult. The only difference is that instead of isolating for acceleration, you are isolating for the time. That was the only difference, okay? But the isolation process is almost the exact same. Luis,
Yes, I have a doubt on exercise 2.
in the exercise 2, from which page?
From page, I don't remember the page, but it's from the homework.
Well, yeah, but it said there are 2 exercises too, so I don't know which one is. So maybe if you want to ask me later in WhatsApp, I can help you with that.
Okay.
Or okay, guys. That is the last topic that we see about kinematics in horizontal motion. Today, we're going to start with vertical motion. As I was saying, we are going to start seeing a new topic that is called free fall. And that is almost the exact same topic, but instead of moving horizontally in the ground, it's objects falling. Okay, it's going to be about objects falling. So I'm going to share the screen. No, this wasn't the screen. Okay, this is in your textbook. Okay, but anyway, it says one of the main objectives in this type of in this topic that is falling objects or free fall is you're gonna calculate displacement, velocity, and also time. Okay, but in this case, it's gonna be on a freely falling object, an object under free fall. You know what free fall is? In Spanish, it's known as caída libre. Caída libre, free fall. It's when an object is just falling down. So when you fall down from your bed, when you're having a nightmare, you just fall down. Well, I'm sorry. You have known one of our greatest enemies, that is gravity. Okay, gravity is an acceleration that all of us are being affected by that acceleration. That's why we are able to walk on the ground. Okay, For example, in the moon, there is a different value for the gravity. The acceleration of the gravity is different in the moon. That's why when you see movies about space travel or that astronauts go to the moon, you see that for them it's like they're like kind of floating in the air. That is because of the acceleration. The gravity over there is less than the one that we have here on Earth. So in this picture that you see over here, okay, free fall in a vacuum, it says when there is no air resistance, all objects fall with the same acceleration regardless of their masses. So every year, well, this is a demonstration that I will show you there in class, only for you to know. Okay? So what happens here in the figure is a leaf against an apple. Okay? The two objects um, are falling down at the same time. So you can see that the picture gets to capture the leaf and the apple. Okay? And what happens? They are next to each other. It doesn't. The apple, you know, that is a lot more massive than the leaf. Okay? It's heavier. Okay? So what happens? You might think that the apple is going to reach the ground easier or faster, but in the end, it's not. The only thing that is affecting objects to fall down at a different velocity is what we know as air resistance, resistencia al viento. According to the shape of the object, an object can be affected by air resistance or not. So what happens with these freely falling bodies? We are all affected by this same acceleration that is known as gravity. For us, here on Earth, the acceleration, okay, the magnitude of gravity is going to be 9.81 meters per second squared. That is the value of the acceleration that all of us experience only because we live here on Earth. If we change of planet, the gravity is going to be different. So anytime that I talk to you about gravity, you have to remember this number. Gravity is going to be 9.81 meters per second squared. For this kind of exercises, we're going to disregard what I told you before, the air resistance. Because air resistance is going to cause the objects to be affected by it, and it's going to take longer for them to reach the ground or not. But here, for physics, ideally, we're going to consider that air resistance is going to be disregarded, but we're not going to consider it. So, what is free fall? It is the motion that all objects experience when they are dropped. Okay, friends, it happens to me every day in a class. My marker falls down. Every single day it happens. I wish it couldn't it didn't happen anymore, but it's always going to occur. One, because I don't have sticky hands, and number two, gravity is always there. Gravity is always there. So gravity is the responsible for you falling down and you hurting yourself. Okay, you were running probably, and you are more responsible than gravity in this case. But my point is, if you fall down, falling down is exactly going down. Okay, you're not going to float when you fall down. That's my point. So all these objects are going to experience this constant acceleration. So what formulas are we going to use for this topic? We're going to use the exact same formulas that we have been using for a uniform or constant acceleration. The only difference is that the acceleration here is known, is 9.81 meters per second squared. Okay. Oh, I didn't paste the exercise. I'm probably the dumbest person. I didn't paste the exercise. So take a look. Sample problem F. Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upward. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? So take a look for these exercises. As you're going to be able to notice, the recognition of the data is the exact same way that we did before. We need to start recognizing our given. So in this exercise, what is the initial velocity of the object? First of all, which one is the object? Let's analyze the exercise. Which one is the object? Which one is under free fall?
The volleyball.
The volleyball.
The volleyball, okay?
Volleyball.
Jason, yes, he's mentioning the problem is the one responsible. But the object that is under free fall, free fall is the volleyball. Okay, so this volleyball moves with an initial velocity of 6 meters per second. It says straight upward. And here, my guys, we're going to start using the symbols. Okay, remember what we said in the beginning of the school year. If an object goes up, is the sign going to be positive or negative? Do you remember?
Positive.
So when an object goes upward, we're going to consider a symbol positive, and when it comes downward, we're going to consider a negative symbol. Okay? So what we know about this volleyball is that it has an initial velocity of 6 meters per second, and it says upward. Okay? So I specified the direction. Then it says, if the volleyball starts from 2 meters above the floor, this data is very important. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? So what's going to happen in this exercise? I know they already started with the music. Okay. So here's the ball. Okay, here's the ball. And it says that this volleyball initially was at a distance from the ground of 2 meters. And what happened? This Jason guy, he hit this volleyball that this one moved upward, okay, with an initial velocity of 6 meters per second. What is going to happen? Is this volleyball going to continue going upward until it goes to the moon, for example, or is it going to return? Is this volleyball going to return to ground?
It will return.
Yes, they will return. The reason is they return because of gravity. Gravity is going to be the acceleration that is going to be pushing objects down with a fixed value of 9.81 meters per second squared. So it doesn't matter. It really doesn't matter. It says you're killing me. My eyes.
Sorry.
Of course I'm joking. It didn't affect me, but you are distracted. Um, so what is going to happen, guys? All I want you to understand is this kind of motion. That it doesn't matter how hard Jason hits the volleyball. The volleyball is always going to return to ground because it is affected by this value of gravity that is known as 9.81 meters per second for n. It is an acceleration. Okay? As you can see, it has units of acceleration, so gravity is going to, in the formulas, gravity is going to replace what we used to use as acceleration before. So it's going to be the same formula, but instead of acceleration, it's going to be gravity instead. Remember to copy the